Hello everyone, welcome back to this webinar series on Kubernetes. This time we're going to talk to you about storage and persistence. Let me make sure that we are logistically set. I hope all of you are able to hear me and also see my screen. So if you have questions, feel free to type them in the questions bar on the GoToMeeting control panel. So let's get started. My name is Janaki Ram. I'm a Google developer expert based out of Hyderabad, India. I'm currently a market research analyst, an advisor to startups, and also an architect working with a few enterprises. So we have been running this series for the last 6 months. In fact, in the new year, we'll be delivering our first webinar, which is the 6th webinar in this series. And we have been covering quite a few topics. My friend and the co-speaker, Joseph, is not joining us today, but typically he is the co-host or the other speaker for this webinar series. So the entire series is focused on helping you get started with Kubernetes. We are going to bring you experts from the container ecosystem, not just me and Joseph, but expect to see additional speakers and more experts joining us in the upcoming webinars. Each webinar is focused on a specific concept that will help you accelerate your learning of Kubernetes. We don't expect many prerequisites, but understanding Docker would help you. And we try to give away a $100 GCP credit to all the attendees. We have been having some issues, so I want to make a disclaimer that it's going to take some time for us to send you the credits this time. We are working closely with Google to sort that out, but we ran into an issue where some of the credits have been invalidated. So we are fixing that. So expect some delay before we send you, but everyone will get a $100 GCP credit. The recording of this webinar will be available at cube.live, where you registered. And that's going to be the landing page for the recordings as well as registering for the upcoming webinars. So like most of our past like most of our past webinars, we are going to take one topic and go deep into it. So this time we are going to discuss how to add persistence to pods. How do you deal with block storage available in the cloud, public cloud, like Google Cloud Platform or Amazon Web Services or Azure? And taking that concept further with persistent volumes and claims. And of course, like every webinar that we deliver, we also have demos to drive the point across. So let's get started. If you have been familiar with Kubernetes, you know that pods are ephemeral and they are primarily stateless. Since pods can be scheduled on any node, and particularly when they are a part of a replica set, they may get recreated and scheduled in any of the available nodes. We should make the pod stateless. That gives us better scale and portability of pods across multiple nodes. But not every workload is stateless. Any meaningful application will eventually deal with data, and data needs to be persisted, and persistence is very, very important for web scale applications and enterprise applications and any other meaningful line of business application. So to support state and to make pods more stateful, Kubernetes has multiple strategies. At a high level, there are 3 ways of bringing persistence into your workloads. The first one is the basic volume, which will add persistence to your pod with some limitations. The second strategy is to rely on distributed storage like NFS, Ceph, Gluster, or block storage in the public cloud, and create volumes that are based on these robust storage backends, enabling developers and DevOps teams to claim the storage. Those are the persistent volumes and persistent volume claims that we're going to see. The third strategy what we'll discuss in the next webinar is configuring your workload or a part of your workload as a stateful set, which was formerly known as a pet set. So we will take a closer look at the first two strategies, which include dealing with volumes and dealing with persistent volumes and claims. So if you're familiar with Docker, you will realize that Kubernetes volumes are very similar to Docker volumes. But that's where the similarity ends. In terms of lifecycle, in terms of management, in terms of what is really expected, they are very different. And as we know, a pod is a boundary for multiple containers. And once you attach a volume to a pod, all the containers will have access to the underlying volume. This is very useful in scenarios where you need to have multiple containers read and write to the same mount point or to the same persistent backend. One example is you would actually have a web service, a REST endpoint that is used as ingestion endpoint by multiple clients which are uploading images or logs or sensor data or anything. And then you have an Nginx container in the same pod which is responsible for showing the real-time data which is written to the disk. It picks it up and shows a graph or renders the static data as a HTML page. So those scenarios make it very useful for when we are using single volume shared across multiple containers that belong to the same pod. Volumes are typically associated with the life cycle of a pod, and this is a fundamental difference between a Docker container and Kubernetes pod-based volumes. So in a Docker container, when you attach volume, you have to explicitly delete that. In majority of these scenarios, the volume is associated with the life cycle of pod. As we're going to see in some implementations, if you create a volume as a part of the pod, and when the pod is terminated, the volume can also get terminated in certain scenarios. Of course, there are mechanisms to completely decouple volumes from pods, which will give us high availability, redundancy, and durable storage. But in some cases, volumes get deleted when a pod is terminated. Mind you, it's not the container. You can restart the container within a pod, but only when the pod is terminated, the volume gets erased or will be reclaimed. Directories in the host can be exposed as volumes, but this is limited to certain use cases. They are also called as the host-based volumes, which we'll touch upon in the demos. And these volumes can go beyond the host-based volumes. They can be backed by a variety of storage choices. For example, NFS, cluster, Ceph, and block storage devices that we have discussed, and so on. So to give you an illustration, if this is the Kubernetes cluster and one of the nodes in which we are running two different pods, and each pod has two containers, when we mount volumes at the pod level, they get available to each of the containers running within the same pod. And the volume is dedicated to each pod, and it is based on the host file system. So this is the common scenario, and this is typically used in dev test environments where durability is not very important. But if you really want to go beyond this, you can actually use block storage or distributed file system, which is independent of the underlying compute infrastructure. It's a separate storage infrastructure that you're going to expose to the Kubernetes cluster, and all the volumes would be based on the distributed storage or distributed file system. For example, if you already have a NAS or a SAN and you want pods to take advantage of that, you basically mount that endpoint in every node, and then you create a storage backend based on the centralized storage, which is exposed as a mount point to each of the nodes, and then you expose it to each of the containers running in a pod. So at a high level, you can classify the volume types into host-based, which are very specific to the host on which the pod is running, which is not very useful in production scenarios, but this is certainly applicable to a few use cases. We'll revisit that in a second, but let's understand block storage. Now, block storage is typical EBS, GCE, persistent disk, or Azure disk, vSphere volume, or Cinder, OpenStack Cinder. So any of those are basically the block storage devices on which you can create a volume. You can also use distributed file system, and the cloud providers have started to expose a managed file system in the form of Amazon EFS or Azure file system. You can also leverage that to create a mount point and expose that to the pods. Apart from these, there are also specific plugins that are written exclusively for containers. Flocker is one of them. Qbyte is another example. You can also use GitRepo as a file system on which you can base the volume. iSCSI is another type. So there are multiple storage classes that you can utilize when you are exposing persistent backend to the Kubernetes pod infrastructure. So let's spend a minute on host-based. If you are running Minikube or a local cluster and you want to basically use the underlying storage for dev test, host-based is very, very simple to get started. So the first one that you would use is called as an emptyDir. So an emptyDir, as the name suggests, is going to be created on the fly when the pod is scheduled on a specific host, and it is available as long as the pod is alive. The moment you terminate the pod, emptyDir will get vanished. What are the use cases? This is great scratch disk option that you can leverage within the pod. For example, you want temporary storage for you to do a disk-based sorting, or you want to write some intermediary files before you process them. So this is more like a scratch disk that is available to you, which is disposed of when the pod gets terminated. The other option is host path, and host path is exposing one of the directories of the host as a volume within the pod. Unlike emptyDir, the host path will remain even after the pod is terminated. And host path comes close to the Docker volume concept, because in Docker volumes you basically expose the host file system directory as one of the internal directories of the container. So host path precisely does that. And the fundamental difference between emptyDir and host path is emptyDir will be immediately reclaimed and completely wiped off when the pod is terminated, whereas the host path will retain the state even after the pod gets terminated. If the pod gets scheduled on the same node and this path exists, it will immediately pick up the previous state. But you got to be very cautious when you are using them in production, because when you schedule pods on any of the nodes, each of them will end up creating their own exclusive host path, which may not be in sync, and every pod will deal with the storage very differently. So until and unless you have a very specific requirement, don't use host path. Of course, host path can be based on NFS, which is perfectly valid. in which case you're actually exposing an external mount point and not an implicit file system directory that is specific to a node, which is fine in most of the cases. But if you are using a supported file system for Kubernetes, then you should be using the storage class that is specific to the Kubernetes infrastructure. And the storage class is more durable, reliable, and designed to be more scalable than host path. And the advantage is it's like a driver. So instead of using a generic driver, you would actually use an optimized driver that gives you better throughput when you use any of the supported file systems. Same thing with block storage. And the storage classes are only growing. So if you keep checking the GitHub repo and the ecosystem, you will actually see many plugins and many storage classes showing up with support for Kubernetes. So we have seen this, and now it's time for me to jump to the demo and walk you through the two strategies. One is the host-based volume, the other one is a block storage-based volume. So we'll start from the ground up, and we'll actually add persistence to one of the pods based on host, as well as we will provision a disk in the cloud and deploy our pod on top of that. So let's get started. Looks like there is some issue with audio. I hope it's better now. It's getting better. But let me take you to the command line. All right, so a bit of background on the infrastructure. I have a local setup that's running, which is based on Kubernetes 1.5, the more recent version. And I'm running one master with 3 nodes. So what I want to do now is to add the first strategy, which is the host-based persistence. So let me show you that. So what you're seeing on my desktop is a pod definition. So it is a Kubernetes object type pod. I call this Nginx. Obviously, it's running an Nginx container. I expose port 80. But the most interesting part of this YAML file is the volume mounts section. So here, I'm actually using mount path, the path that I want to map within the container, and the name of my volume. So that is my vol. And just below this, I'm going ahead and creating the volume called my vol, and the type is host path, which means it's very specific to the node on which the pod gets scheduled. And the path that I want to expose to the pod from the host is varlib my data. So when you actually schedule this pod, even if the directory called my data doesn't exist, it gets created as a part of the scheduling process. So after that, you can actually start using the underlying storage. Okay, some of you are still reporting that the audio is a bit distorted. Okay, unfortunately, this session is getting recorded and I can't plug out my mic. So hopefully it will get better. I'm tweaking my audio a little bit. So, all right, so coming back, this is a classic Nginx pod with just one addition of volume mounts. So let's deploy this and check the status. So before that, let's see if we have any pods. So there are no pods. I will go ahead and create the pod, which is pod vol local. And this goes ahead and provisions or rather schedules my Nginx pod. So let's get the pods again. So now this is running. Let's also probe a little bit into the pod provisioning by using describe pod command. And this shows us some interesting insights into this pod. So first thing, this is scheduled on node 3, Kubernetes node 3, which is something that we need to remember because we are going to now SSH into that node and see if the directory is created or not. That's the first data point that we need to make note of. Second thing is, here there is user share Nginx HTML from my wall with read-write access. So this is another confirmation that the mount point is available within the pod. It also describes the volumes. So this is the host path type, bare host directory volume, varlib my data, and remaining is an indication that the pod has been scheduled within the node. Everything is fine. So now what we'll actually do is come to the cluster, and I'm running a Vagrant cluster on my powerful machine that's running on SSD and 32 GB RAM. So this actually shows me that there are 3 nodes and 1 master, which matches our kubectl get nodes command. So this is directly mapped. If you remember, our pod was scheduled on node 3. So let's go ahead and SSH into node 3. All right. So if you recall, we have gone ahead and declared this as our host path. So let's cd, and you will see an empty directory. So now I'm going to create hello from host, and let's put this in index.html. All right. So now we have the default HTML page within the Nginx pod. Let's do something more interesting. So now I'm going to use kubectl exec it, which is for interactive terminal, Nginx followed by the bin bash command. This will drop us right into the shell. So this directory on the host, varlib my data, is mapped to this folder within the pod. So let's get into that. Okay, so now when I actually do an ls, you'll see index.html. Let's also do a curl localhost because I'm inside the pod. Curl is not installed. This is not a part of the Nginx container. But seeing index.html, that's an indication that it's working fine. So I'm not creating a service because you know how it works, and the objective is to show you storage and not how to access external or internal services. So now if you actually do a cat, it says hello from host. Now let's override this. So hello from pod, and I'm going to write this into index.html. All right. Now we'll come back to the host and do a cat of index.html. So now the pod is able to access the directory that is exposed by the host. This requires root permission for read write. So that is another clause. So your pod will actually, it needs to have root access when it is accessing the host path. That is the prerequisite for you to use host path. Now let's leave this as it is and terminate the pod. Okay, so kubectl delete pod wall local. So now the pod is gone, right? Let's go back to the host and do an ls. So index.html is still around, indicating that the data is persisted. Now, next time when we actually schedule the Nginx pod, there is no guarantee that the pod will be scheduled exactly in the same node and will access this. It may go to any of the other nodes, node 1 or node 2, in which case it will end up creating a new host path and it starts with a blank slate. So that's the reason why you should be very cautious when you're using host path based volumes. You have to do some workarounds if you want to make sure that the data is in sync. For example, running an rsync in the background, which is a very clunky way of keeping data in sync. Or you could actually use an NFS based backend, which will ensure that there is a common fabric, a storage fabric that is being exposed to all the pods. But you get an idea. So that's the quick local volumes demo. Now let's repeat the same thing on the cloud. So for that, I need to switch to my GKE setup. So let me show you what I have here. So here I have a cluster up and running in the cloud with 3 nodes. And what we're going to do is create a persistent disk on GCP and then mount the pod on top of the persistent disk as a volume. So first I need to switch the context. So I'm going to use this command, kubectl config use context. And now when I actually type kubectl get nodes, it immediately shows me the cluster information from GKE. And let's see if there are any pods. There are no pods. And now we need to create a volume and then create a pod. But how does this look like? So let's switch to another definition. Everything remains same till here. But instead of creating host path, I'm using GCE persistent disk, giving the persistent disk name my data disk, and I'm instructing the storage driver to go ahead and format it with ext4 file system. Those 2 lines make a huge difference, and this is fundamentally different from what we have done here. So instead of host path, we are using the GCE PD disk definition, and we also give the PD name followed by the file system. Everything remains the same. But even before we go ahead and provision this pod, we need to ensure that the disk is available. So I'm using the gcloud CLI to create a persistent disk in the cloud. So gcloud compute disks create a standard disk of size 10 GB. And this will very quickly, thanks to the lightning fast response of Google Compute Engine, we'll have the disk created in no time. So now we have provisioned a new persistent disk in the cloud, and the name matches the YAML definition that we have here, my data disk. That is the prerequisite. So with that in place, let's create the pod. So instead of local, I use pod vol cloud.yaml, and now it gets created. So let's give it a minute for the pod to get completely ready. But meanwhile, let's check the information by calling kubectl describe pod nginx. Okay, so now let's start from here. So this is the node on which it is provisioned. Of course, we don't really care about this because the nodes can be terminated and they can brought back. So that's not a concern. Volume mounts. So user share nginx HTML is coming from my wall. At this point, we don't know what my wall is, and we have read-write access for it. But if you come down further, you'll actually notice that my wall is of type GCE persistent disk. The name of the disk is my data disk, and file system is X4. This is the metadata that we have passed from the YAML file. So that's how it is basically mapping the underlying persistent disk to the volume within the pod. All right. So now the pod is up and running, and you know the drill. It's exactly the same. So instead of the local volume, you will now have the my data, the file, the location, which is user share nginx HTML, comes from my data disk. So that's pretty straightforward. Now, when we delete the pod called nginx, the persistent disk is not going to be deleted. So it will still show up here. So let's check by going to compute engine disks. And when you actually look at the available disks, the data persistent disks in GCE, you'll notice that the my data disk is still available, right? And this needs to be manually deleted because the current workflow doesn't include deleting the disk, even if you instruct, and there is a reason for that. So you never want to mess with the durable persistent data stored in a block storage volume, because later on the same thing can be leveraged by other pods when they get scheduled, and that is the fundamental difference between the host path and my data disk. So my data disk is now going to be attached to the node on which the pod is going to be scheduled, and whatever data is available within that persistent disk will automatically becomes available to the pod. But again, this is not really distributed because you can only attach one persistent disk to one node at a time. So it still doesn't give you multiple read-write access or a distributed storage setup. So that is another limitation. Even in public cloud, the only way for you to make sure that all the nodes are accessing the same data, you need to have a cluster kind of file system setup. All right, so let's go back to the slides. So we saw host-based volumes, particularly the host path, and we briefly discussed the difference between the emptyDir and host path, and we also looked at how to provision a persistent disk in Google Cloud Platform and utilize that for the creation of a pod. All right, so let's move to slightly advanced concept. When you are attaching volumes to a pod, it is still very implicit. It is very similar to what you would do with a Docker container. But in production environments, and particularly in an enterprise scenario, there is a specific workflow followed by sysadmins, ops teams, and developers. So in a traditional environment, developers will not have access to the building blocks or the infrastructure primitives. They never deal with compute, storage, and networking directly. Instead, they request for those resources. Sysadmins and the ops team are responsible for making those resources available to developers. So if you're a developer in your organization, you go ahead and place a request for a new server or a new environment or a new NAS storage endpoint, but you never directly get access to that. Kubernetes is highly aligned with that workflow. The best thing about Kubernetes is the separation of concerns. Once an enterprise deploys Kubernetes, they can start following the existing governing policies, workflow, and the routing policies that they already have. So to facilitate that, Kubernetes uses a concept of a persistent volume and a persistent volume claim. So a persistent volume is a networked storage in the cluster that is pre-provisioned by an administrator. So this is almost like saying every user's desktop will have the home directory with, let's say, 1 GB. So that is pre-provisioned, And when you log into your desktop, a script runs to mount your home directory, and you have a maximum limit of 1 GB on it. So who defines that 1 GB? It is the administrator. So similarly, in Kubernetes, the administrator will create a persistent volume which is pre-provisioned, and he will allocate a quota for different developers, groups of developers, namespaces, organizations, any specific unit that he's going to deal with. Once this pool becomes available, it's going to be claimed by developers or users. For example, a persistent volume could be of 5 GB, and the claim could be 1 GB, which means you are now consuming 1 GB of the available quota. And other user, when he creates a persistent volume claim, he is going to claim another 1 GB. And users or developers can keep claiming till the quota gets exhausted. Even one user can go ahead and grab all the available 5 GB. But the limit, the upper limit of 5 GB or 10 GB or X GB is going to be defined and allocated by the network administrator. Storage classes are the storage profiles selectively offered by administrators. Kubernetes may support dozens of storage classes, but an organization could be very sensitive to what kind of a file system, what kind of a storage backend that they would want to use. So an admin selectively decides what kind of a storage class is going to be made available, and how it is mapped to a quota, and finally how developers and users can claim a slice from the available pie, which is the storage allocation. So I'm borrowing a graphic from Red Hat. So if you actually look at the workflow, administrator registers persistent volumes in a pool. So he will create a pool of persistent volumes mapped to NFS, iSCSI, GCE, and so on. It can be any supported storage class type. The developer comes up and claims a persistent volume from the pool. And once he claims, he gets a reference that he is going to use in the pod. So this is no different from the way you ask for a VM, you ask for a physical server, or you ask for a specific port to be opened. The beauty of Kubernetes is it respects the existing enterprise workflow and the governance and the policies that are already established. So it just falls in line with the existing workflow. If you look at the life cycle of a persistent volume, it gets provisioned. This is where the administrator will create a chunk of storage block, and then it gets bound. A claim is nothing but a binding commitment between the user and the storage chunk that is allocated, that is available. Once it is bound, applications or pods will start using them, and once a pod gets terminated, it gets released, and after that it gets reclaimed, which means it goes back to the pool and it becomes available for binding all over again. So this is how home directories in a VDI environment or in a traditional networked workstation environment will be configured, and Kubernetes follows exactly the same paradigm. So let's take a look at slightly advanced concept where we go ahead and create an NFS based persistent volume, and then we claim it to mount a pod, mount the volume inside a pod that utilizes that. So let's switch to the command line or the editor first. So I am the admin, and now I'm going to create a persistent volume. So when I create a persistent volume, I decide a few things. For example, what is the name of my persistent volume? This is very important because this is how claims will be associated. I add additional metadata in form of labels and annotations. Then I define the capacity. Here it is roughly 1 GB of storage that I am allocating. Access mode, read write once. This will enable pods to read and write to the underlying file system. Persistent volume reclaim policy is recycle, which means it gets returned to the pool. And this is where I define the supported storage class. In this case, we are using NFS. The path is the exports section of your NFS, which is optdata/web. This should be existing. This should be created before you go ahead and provision your persistent volume. And you give the server address. So this is the master server on which I have configured NFS. So once I have this in place, then a developer steps in. He doesn't know what is the storage class, and he need not know. He doesn't even know whether it is NFS and what is the server and other details. He just needs to know the maximum available pool size. Otherwise the persistent volume claim will fail. So he comes here and then he creates a volume claim. Access mode is read write once, and then he says, give me 1 GB of the allocated chunk, which happens to be 100% of our allocation. And once this succeeds, it becomes an available persistent volume, after which he moves to the pod, and here he says my claim is my PVC, which links back to our persistent volume claim, my PVC, and name of the disk is my PD, and it is pointing to this mount path. Pretty straightforward. The only difference is here we are actually using a persistent volume claim instead of a host path or a GCE persistent disk or an AWS Elastic Block Store. And Kubernetes infrastructure is smart enough to figure out that you already have a claim by name myPVC, and it is bound to the persistent volume called myPV. So it is a cascading effect where the administrator first creates a pool of volumes, then the developers step in and claim that, and those claims are attached to a pod as volumes. So let's go ahead and run this. All right, so it's time for me to switch back to my local cluster because it's more convenient and I can actually show you the internal details of the NFS. So kubectl config use context vagrant. All right, so kubectl get nodes. Okay, now we are pointing kubectl to the local cluster. Now I want to show you the NFS configuration. So now we have logged on to the master node, or rather the master server of Kubernetes. And if you look at etc exports, you notice that I have configured NFS to expose this share called optdata. So let's move to that folder. And there is a directory called web, which already has a file called index.html. This is perfect. Now let's get out of the master and log into one of the nodes. Let's say we log into node 3. And here, when I go to mount /data, you see that there is a web directory. Inside web, we have index.html, and this is the NFS storage backend that we are talking about. So this infrastructure is in place. And the master, for example, if I ping the master, it is available on this IP address. which is what I have used in my persistent volume definition. I hope this is clear. This is one of the advanced scenarios where you actually use an NFS storage class and configure NFS within the Kubernetes cluster and use it within the pod. Okay, so now the infrastructure is all set. So I'm the administrator, and what I'm going to do now, let's make sure there are no PVs available and no PVCs available. This is perfect. So now I go ahead and first create the persistent volume. So persistent volume, my PV is created. Okay, so get PV shows capacity, access mode, reclaim policy, status is available, claim is empty, and it was created 7 seconds ago. Perfect. Now I come in as a developer, and I don't know where the storage is coming from. It's completely obscured. All I need to know is I can claim up to 1 GB. So I now do a claim. So I run kubectl followed by my PVC. And now the volume claim is created. So let's go ahead and get the PVC. So my PVC is bound to volume my PV and all other details. So now let's go back and check the PV. It should show as bound. Earlier it was available. Now it has become bound. That means if I try to create another claim, it will fail because I'm using 100% of the volume in my claim. Perfect. So now it's time for me to create the pod. So my pod gets created. Let's get this. It's going to take a while. It's going to pull the Nginx image and okay, there we go. So now let's do a kubectl describe pod, my pod. Again, the same useful information. The volume mount is coming from my PD, and my PD, we don't know where it is coming from. It is NFS because we also played the dual role of an admin and the developer, but otherwise we never know where my PD is coming from. All right, so now let me look at the container name is web. Okay, so now let's do a kubectl exec web followed by bin bash. Oh, okay, so it is not web, it is my pod because I only have one container inside that. All right, so now this is the path which we are exposing as the mount point. Let's get into that, and we see index.html hello from NFS. So let's create another file, and now we are switching back to the node. So this time let's SSH into node 2 and go to mnt data web, and we have k8s.txt. So this is a perfect walkthrough of all the way from provisioning the storage. I didn't really walk you through all these steps. It's a standard routine way of configuring NFS, but we started from there, and then we created a volume as an admin, and then as a developer and DevOps team, we claimed that space and exposed that to our pod, and eventually the Nginx server started accessing that as well. So that's the entire workflow. All right. Okay, so let me take you back to these slides and summarize what we have discussed. So essentially, if you're getting started with Kubernetes persistence, you got to understand 3 different concepts and terminologies. Storage class, which is basically the drivers and the supported interfaces for a variety of storage backends. That is the first thing. Second thing is the persistent volume, which is used by the DevOps and the developers to create persistent volumes and mount them inside the pods. Then there is persistent volume claim is what is used by developers. Persistent volume is what is created by the administrators. And then every pod implicitly has the volume definition. It doesn't matter where it comes from. It can come from any of the supported storage classes all the way from emptyDir to iSCSI. It doesn't matter. So a volume definition inside a pod can map to any of these choices. So this is a very important concept if you are developing and deploying slightly more mature applications and more real-world applications, because you will have to deal with MongoDB, Cassandra clusters, and sometimes MySQL, and you cannot really deploy a complex application without persistence in the backend. So this is very useful, but that's not all. As you notice, there are multiple challenges involved in running stateful workloads in Kubernetes. What happens if I delete my pod? Or how will I configure a Cassandra cluster or a MongoDB replica set? How will one node, or rather one instance of my database, discover the other? And how do I bring the reliability of replica set where a pod gets terminated and immediately the other one comes up? How do I bring that kind of availability to my stateful workloads? So to address that, the Kubernetes ecosystem has created a concept called stateful set, which was previously known as pet set. And this was made available as beta in the latest version, which is Kubernetes 1.5. And stateful sets will help you configure highly available clusters of relational databases, or for that matter, anything, including a service like Zookeeper or XD or a Redis cluster, anything that requires a stable host name followed by a persistent backend and a well-known endpoint for discovery. So when you bring all these attributes, you essentially create a stateful set. And I'm very excited to share with you that the next webinar, which is on Feb 14th, which is just a few weeks from now, will show you an end-to-end demo of configuring a stateful set, and we'll actually deploy a highly available LAMP application that relies on a MySQL active-active cluster. So we'll cover the concepts of stateful set, and along with that, I'll also show you how do we bring node affinity. How do you ensure that a pod is always co-located on a specific node? How do you bring that? And how do you also implement auto-scaling for pods for your stateless front ends? So horizontal pod auto-scaling is like the auto-scale feature of EC2. Depending on certain parameters and thresholds, you can automatically scale in and scale out the number of pods. We'll also implement that. So the next session will be very few on slides, but heavy on demos. So if you are interested, you can register starting tomorrow. I need to update the landing page with the new link to the registration. That will be done by tomorrow. And you can continue this discussion of persistence and statefulness into the next webinar where we deal with stateful sets. So that's the topic that I wanted to announce. And a quick disclaimer, it's going to take a while for us to get the credits for all of you, but we'll definitely send it to you. I know most of you are eager to get started, and I've been getting mails from the previous users that some of their credits were not working. So just bear with us for a couple of weeks and we'll fix that. All right, so it's time for me to take a couple of questions before we wrap this up. And if you have questions, this is my email ID. Feel free to send me your questions. Okay, so there is a question on what is the alternative to attaching a persistent disk to multiple nodes, because a persistent disk in GCE or an EBS volume cannot be attached to multiple nodes. So you have two choices. One is you set up your own distributed storage based on NFS or cluster, or depending on the public cloud that you are in, you could leverage one of the available um, uh, hosted or managed file systems. So while we are looking at the Q&A, I want you to take a minute and respond to the poll. I really appreciate you attending this, and we appreciate your feedback. So please take a minute and do let us know what you felt about this webinar. All right, I only got 57% votes. I really appreciate if everyone can just click on one of these options. Your feedback is highly valuable. Awesome. So while you are still participating in the poll, let me bring up other questions. Okay, the question is about covering network add-ins in Kubernetes. I'm afraid that's a slightly advanced topic. This is more at the workload level. We are not getting into the cluster management and cluster administration and cluster configuration. So typically, additional add-ons and registering storage classes is very infrastructure driven. We may cover that, but not in the coming weeks. Okay, there is a question on how did the pod became, how did the pod creation succeed when the persistent disk was not formatted. In GCE, even before you use your persistent disk, you got to format it. So that's the auto magic formatting that Kubernetes storage class does. So when you actually use a storage class like GCE persistent disk, and when you mention the file system as ext4, you're actually indicating that you want to format that with ext4 or any of the supported file systems. So as a part of the pre-provisioning, only the first time you are basically accessing that, it gets formatted. So that is how you instruct Kubernetes storage class to format with a specific file system. If you're not using this, and if you're attaching a PD to any of the GCE VMs, then it is your responsibility to go ahead and format it with the supported file system. All right, we are almost at the end of this webinar. Thanks again for all the support and your encouragement and participation. Do keep an eye on cube.live. We are committed to bringing you quality content and help you learn and adopt Kubernetes. So stay tuned for the next webinar. Thanks once again. Have a good weekend. This is Janakiram signing off.